air. It's not just alone soil or water alone, it's the interaction of all the three. So it is very difficult to figure out and find a solution to those kind of things. And because of that, it is very very important to study those things. And how are we going to do that, and why GT principles come in here is, say for example, analyzing the failure of foundations, designing a safe land disposal, you know containment for wastes, maybe municipal solid waste, or hazardous waste. That has also become a very very huge problem nowadays, especially in developing countries like India. Assessing contamination and containment of the polluted
நல்லா
sites.
பேசுவான்.
So it may be industry sites, or it may be other sites also, like nuclear
கன்னடால
sites,
படிச்சேன்,
or
அதனால இங்கிலீஷ் நல்லா பேசுவான்.
many many other things. So the principles of our geotechnical engineering or soil mechanics is used in these applications to determine the parameters, and then try to design or try to apply these things in a very very effective manner. So if you come to applications, I don't have to what to say tell you this. So uh, if you
ஊர்
take
ஒன்று எனக்கு
geotechnical
தெரியாது.
engineering, it is like it's like applied into everywhere. If you start from structural, yes, it is linked to structural. It is linked to transportation. Principles are applied there. Construction, environmental engineering, earthquake, yes, hydraulic engineering like dams, groundwater drainage, marine geotechnics, mechanical, rock mechanics, etc., geology, geological engineering, geomaterials, hazards, etc. So all these things come into picture, and all these things have a very close relationship to what to say geotechnical engineering. So if we take the applications, let us check, or let us take the cases of what to say waste here. How the geotechnical principles are applied into waste management, or effective waste management. Now you might be wondering why it has to be waste. Why municipal solid waste? Because uh, some time back, like close to 5 to 10 years back, waste management was such a big issue. We didn't have any
இப்பதான்
solution,
சாப்பிட்டேன் சாமி, நான் மீதி
and
எடுத்துட்டு வந்துட்டேன். அங்க இருந்தது
the
அதை
issue was
இப்பதான்
so
சாப்பிட்டேன்.
rampant that everybody was running here and there to find a solution, and how to sort it out, what to do, and all those things. So we at IISc were the first ones to study the engineering properties of municipal solid waste using the geotechnical principles, and determine all the parameters, and finally effectively design, like a containment system based on that. Though these things were like available, or there were these things were being done at a very what to say normal level in the foreign countries, in India it was still to be explored. So what we did is, like we tried to use these principles to determine the properties, because as you know, municipal solid waste is a very very heterogeneous material, and it is not easy. As you know that geotechnical principles deals with mostly homogeneous material like soil, sand, etc., right? So we tried to do that. Now when it comes to waste, what are the properties that we knew at the time? It's like just the basic physical properties or the composition, like what it contains. Maybe different types of waste, like plastics, or some cloth like material, some inert like material, some soil like material, some organic content, etc. But then when all these things come into one, or get mixed into one, it becomes a proper cocktail, which is very difficult to dispose, or which is very difficult to treat. So that is when we tried to get in geotechnical principles. So what is that further? Geotechnical principles means what tests we did, what and all experiments we performed in the field as well as in the laboratory, and what did we arrive at. I'll just take you through this journey, and also finally give you the applications using this principle, how it can be done. Like I said, let us take the classic example of waste. And what you see is a landfill. Imagine the height of the landfill. This is a landfill in Delhi. It is known as Ghazipur. The height of this landfill is almost 70 to 80 meters. So you must have seen a lot of what is issues with respect to the failure of landfills, with respect to the stability of landfills, with respect to the leachate that is coming out of the landfills, all these things. So people were clueless. So this was one such thing that had come to us, and we had taken up this as a challenge through a DST project that we would find out a solution. So there were multiple issues. One is with respect to the stability. It used to collapse. Then there were like issues of fire. It's like rampant fire. It's like not anyone deliberately putting fire, but then it is kind of fire on its own. So along with that, seepage, leachate during the rainy season. So if you see all these things, some way or the other, connected to our geotechnical engineering or principles of geotechnical engineering. So that is how it was decided that we'll try to see or address how it can be done. So this is like you can see the mountain of garbage here. So like I said, all these, why I'm showing this picture from a top view is you can see all the what to say houses here and all those things. One minor collapse and all these people will be gone. This is like basically the areas that is surrounding the landfill. It's like a slum, and then one minor slip or instability issue, it will destroy all
பட்
the
அது
houses, and then
ப்ரெசன்டேஷன்
it will
தெரியுதுல்ல
become
உங்களுக்கு?
under the like a slide. Like whenever the
தெரியலையா?
landslide happens, it completely engulfs everything, whatever
தெரியலையா?
is beneath it. Something like that, the waste would engulf that. So we had to prevent it, and then
செக்
give
பண்ணுங்க. ஒரு ஸ்க்ரீன் ஷேர்
suitable
ஆயிருக்கு.
suggestions or designs to prevent that. So you can see that this is on top of it. Like I said, the fire also is an issue. So there, it's fire means it's not complete fire. It's like smoldering like this. It will be like slowly burning, and then there'll be smoke coming out
இருங்க,
of
நான்
it.
வெளியே போயிட்டு உள்ள வரேன். சரியா போயிரும்னு நினைக்கிறேன்.
You can see this. This is at the top of the
இல்லை,
landfill.
நான் லீவ் ஆனோன்னா எப்படி இருக்குன்னு தெரியலையே.
Now, coming to the status of municipal
ப்ரெசன்டேஷன்
solid
வருதுன்னு
waste
மட்டும்
landfills
பாருங்க.
in
என்ன,
India,
நான்
it
வேற
is
யாருக்கு கால் பண்ணிட்டா?
good to know before we start what was the issues and how it happened or what is the thing. So, when we just analyzed these things, we came to know that around 70 to 90% of the urban solid waste is being disposed of into the landfills, and most of the landfills are not scientific or non-engineered. So, urban India generates around 65 million tons of waste, and it's predicted that by 2030 it would increase one to 165 or 170 million tons. And out of that, 43 million tons of waste is
சொல்லுங்க
collected
லோகேஷ்.
annually, which out of
தெரியுதா?
which
ஓகே.
31 is dumped in the landfill, and just 11.9 or 12 is treated. 12 million is treated. So you can imagine the scenario or situation or the seriousness of the situation. So coming to the other facts, landfill ranks the third major source of anthropogenic methane emissions. So this methane emission is one of the major factors for this fire. Why methane is having 28 times more global warming potential than carbon dioxide? Then waste, bio earth, or waste like material is very toxic. It's not suitable to be used as a fertilizer also, as long as or as far as you treat it properly, only then it can be used. The biomining practices are leading to toxic waste, uh, called bio-earth accumulation, which is again leading to further issues like microplastics or contamination of other stuff. So urgent need of cost-effective technology to utilize this also was one of the what to say primary objectives. So like I said, what is waste? It's a heterogeneous mixture of materials that is generated in the urban area, which does not have any further use in the society. So they all dispose it, and as you can see, it is a proper mixture of everything. It is very difficult, and as the day progresses or as the time goes on, it just degrades, and then some of it degrades, some of it degrades slowly, some of it degrades very lately, some of it doesn't degrade. So we are dealing with such kind of materials. So coming to these what to say tests and techniques, what we thought is like since this material is getting degraded as the time progresses, like after a couple of days when it is dumped in the landfill, the properties or the size of that gets reduced. I'll tell you what happens in the process is like once you dump it there, the larger particles or the particles that are greater than 100 centimeters or 100 that is 10 centimeter are being picked up by the rack pickers. Whatever is left out is less than 10 centimeters or even further below that. So if we study the properties of those materials, I think we would be able to come out with a solution properly, because that is the one that they cannot take, and then that is not recyclable and all those things. By the way, this retail industry of rack picking industry or rack picking is a huge industry. It's worth millions and more than that. So what basic parameters we started is that like particle size distribution. So again, we use the sieve analysis, the density, we use the density method, econometer method, shear strength, both direct shear and track shear tests, compressibility. So you have your what to say, odometer test. So along with that, we also try to do some permeability test. We also try to do some stability uh, analysis, slope stability analysis using dynamic properties. Again, for determining dynamic properties, cyclic traction tests were used in the laboratory. Even field tests were used. Field tests were used for determining the what to say, shear wave velocity in the field using a MASW multiscale spectrometer, spectral wave analysis. So I'll explain you that and what it is and how it is being used. And of course, in the laboratory, we do this hydraulic conductivity or permeability, this thing set tests to determine the hydraulic conductivity of waste and the soil. And then settlement through compressibility test, and then slope stability. So if you see overall, unless and until we determine these things, we won't be able to effectively design a proper containment system for this waste. So to start with introduction, I think I've said most of the things. So like it contains like materials like papers, plastics, glass, metals, fine, earth particles, etc. It's a proper mix of everything. So we started with the basic index engineering properties of MSW, like we do in the geotechnical engineering or soil mechanics, and then detailed study of the compressibility of the waste. So we started with the physical composition. We started to analyze what is the physical composition. We collected some samples, like quantity of waste was like close to 100 kgs, and the age of waste was around 4 to 5 weeks. By that time, it was kind of partially degraded, and then that was used. And whatever waste we brought was passing through a 100 mm trommel. Trommel is nothing but a sieve with 100 mm pore size. So we started with that size, and then we partially came down to less than 20 mm size, using different sieves, like 100 mm sieve was used, or trommel was used, then consequently 75 mm, then 35 mm, then 16 mm, or 20 mm, likewise. So what the analysis is that whatever we got is more was below 20 mm size. So further, again, for the further 20 mm passing materials, we, that is waste, we conducted all the experiments. So if you see here, you can see plastic, clothes. 55 percentage is like earth like material or your organic content. Then other components are also there. So this we performed it at the site, and as well as we brought it into the laboratory. I'll further show you what is the particle size distribution in the next slide. So next is total volatile soil. It is nothing but the organic content of a material. So this comes in handy. These principles comes in handy where when we are dealing with organic soils like peat and all those things. So these kind of tests are very useful. So again, the same thing was what to say, adopted here from there, trying to see how much of organic content is being present in the waste. So the standard thing is like keep the sample in the oven, or you keep the sample and raise the temperature to 105 degrees, and whatever is left out after 24 hours is like the moisture content. So in this case, it was around 44 percentage. Then if you have to find out the organic content from 105 degrees to raise the temperature from 105 degrees to 550 degrees in the muffle furnace, and whatever is left out is the what to say, your whatever goes off is the organic content, something like that. So the weight loss, or the the material that is gone. So you weigh the sample, the weight of the sample before and after the test, and finally you say that this is the what to say, percentage. So in this case, the organic content was around what to say, uh, 46 percentage, and the rest was around 54 percentage, that is inert. So if you can see that it's a proper mixture of almost 50-50 kind of thing of organic content and the inert material. Now the problem here with us was, if you take this 50 percentage of organic content sometime or the other at a later point, it is going to degrade, or it is going to reduce in volume. It is not going to be stable. The 54 percentage or the 50 percentage of the inert is going to only stay there. So accordingly, we have to, what to say, study or work out. because this thing was very important. The same thing happens when you deal with organic soils. So now coming to particle size distribution, all these things were tests were performed to as per the ASTM standard. So 60-minute what is SC analysis was performed. Again, the standard sample size was 100 grams, and then the CCCU values, that is coefficient of what to say, the CCCU values were calculated, and it was like 15 and 1. It was like, understood that it is well graded and absence of any coarse material in that. So this is a sample, I mean, like test. You can see that most of the things were passing through the 10 mm. See, when after that further, this is the distribution how it was. So you cannot imagine that as the waste degrades, the size of the waste particles reduces. That's why we took it from you know uh, 20 mm. Difficult to find out what to say, what is the organic content. So sometimes if there is no provision of determining the organic content, you can just measure the specific gravity and determine the organic content. That is, in this case it was like around 1.33. If the first specific gravity is more than 2 or 2.5, then you can say that it is not having that much of organic content. But if it is less than that, then obviously there is some amount of what to say, organic content in that, which needs to be dealt with properly. So here the picnometer and the density bottle methods were used, and then it was like as per the ASTM standards, and what we got is almost the average is this. So you can see the waste. So this is the waste particles that was brought from the field, and then it was put into the bottles. Now, coming to this biomethane potential test, why this test is being done is like, here a little bit of knowledge of the environmental field is also required, because the organic content, as it degrades, there are two ways of degradation. One is, it degrades aerobically, and the other thing is it degrades anaerobically. Now, when it degrades anaerobically, methane is produced. Now, why we are doing this test is like, waste, what happens in the field is like, you keep on dumping waste, layer over layer, layer over layer. And during the process, what happens is that once you dump one layer and then 10 layers above that, the bottommost layer, there is no oxygen for that, and then anaerobic conditions prevail there. And once anaerobic conditions, or there is no oxygen there, to be very frank, and then when there is no oxygen, then your anaerobic degradation starts. It's a very congenial condition for anaerobic degradation, and then your methane starts producing. And that is how your methane produces, and when it seeps out of the landfill, creating smoke or fire, and all those problems. So we try to find out what is the potential of the waste to produce methane. That is called biomethane potential experiment. Now here again, there is no standard protocol for conducting the BMP test. So I'll just explain you the and what to say. Now what we have to give there is that would be the food. The organic content would be the food, but for the food to be decayed or eaten by some bacteria or something, we should give them the bacteria also. That is called the inoculum here. So the substrate is nothing but the food, and the inoculum is the bacteria. So here the ratio was, what to say, 1:1. Means that if you have 1 gram of what to say, food or substrate or waste, then you give 1 gram of the bacteria or inoculum, just to see how much of um, waste or food it can consume. So this is that experiment that we designed. You can see that this is the, what to say, bench bottle. This is like capillary tube that is coming from here, and coming into this bottle. So here what we have is the substrate plus inoculum. So we have waste and plus the bacteria. So simple. For that bacteria, we didn't use any hi-fi techniques. We just used cow dung water, because cow dung water has a lot of bacteria. And once the gas starts producing, it will enter through this pipe, and then it will go here, and you can see the gas that is being collected here. And because of that, the water will get displaced into the cylinder, graduated cylinder. So you can measure the gas by this whatever it is, whatever is displaced or water is collected into the cylinder. So this is how we tried to find out, like, if we take, say, for example, 100 grams of waste, how much of gas it can produce or methane it can produce, because it is very important to say or determine how much of gas it will be produced and how it is going to escape from the waste layer. So all those our issues of pore pressure, all those things will come into the picture there. So this simple equation that is called the Compet's equation, that is used to model the rate of degradation. So this is how it is. You can see that initial phase is a what to say settling phase, or the lag phase, means that initially there is no production because bacteria needs some time to mature. And once it starts matured, like starts producing gas, that is the time when your methane starts generating. So initial 15 days or 16 days is the lag phase, and after that the methane starts producing. So you can see that 1 2 3, almost what to say 15 ml. So this experiment was carried out for more than 80 days, and after that I think there is no what to say increase in what to say waste, sorry, the gas generation. And then because of that, it was like we thought we'll stop it. So you can see here, this range of 14 to 16 liters per kg of dry waste. The quantity of methane varied between 29 to 42 percentage. So once we get this, then we know that some gas is being produced, and accordingly, either we have a gas venting system or gas removal system, because it doesn't destabilize or disturb the what to say waste layer when we compact it, and also doesn't failure, it doesn't lead to any failure. It's the same thing. Now, coming to the engineering properties of waste, why this is important is, like, when we are designing a containment system or a, what to say, a proper engineered landfill, the behavior of the waste body or the waste controls many aspects of the landfills, like, the lining system, the performance, including the stability issues, the integrity of the geosynthetic material, because as per the rules, a lot of geosynthetic and lining materials should be used. Coming to the knowledge of waste engineering properties is required to assess the potential modes of failure. That is the most important thing. So, as per this thing, we'll be able to summarize the measurement and interpretation of the parameters, like compressibility, shear strength, or stiffness, hydraulic conductivity, and then apply it to effective designing of the landfills. Now, compaction test. Compaction test, you must be knowing that it's a very common test in geotechnical engineering. Standard Proctor compaction test was conducted in accordance with the ASTM standards. The mold that was used was a separate mold that we had designed. Like, normal mold is of a much smaller size. Smaller size. Here we used 100 mm dia and 125 mm mold, and different what to say mixtures were used, like 30, 40, 50, 60, just to find out the optimum moisture content and the unit weight accordingly. So here in this case, the optimum what to say moisture content was found out to be 45 percentage, because uh, if we design this at a very dry what to say uh, stage, then also there are chances of it being cracked. If we design it at a very high moisture level, then also it will lead to failure. That is why this optimum moisture content is very, very important to know or to uh, design. So this is how it was prepared. You can see the waste, you can see whatever I showed initially, the particles, you can see how big the particles are. This is how it is. So we compacted it like this, and then whatever we got is like this. So you can see around 45 percentage is the what to say moisture content, optimum moisture content, and accordingly the density is around 850 or 860 kg per meter cube. So the takeaway from this experiment is that if we are able to maintain that unit weight, the structure will be stabilized. It won't lead to any failure, like like we all know. So try to maintain that. you know one is either maintain the moisture content at 45, as well as the dry density at that, so that your structure is more stabilized. So that is how we came to the conclusion. Now coming to the permeability or the hydraulic conductivity, because this is very important, because during rainfall or during extreme events such as maybe say cloudburst or something, there'll be huge amount of water that will be released over the landfill, and some of it, all of it will not go off through runoff, surface runoff. Some of it will enter the landfill also. For that we have to, what to say, know what is the conductivity of the waste material that is there. Say for example, if we are compacting that the waste at what to say, this 10.3 kilonewton is nothing but 880 kg per meter cube that we determined in the last uh, experiment. So here the water content and bulk density were maintained at this 45 percentage and 10.3 kilonewton per meter cube. And the mold that was used was 50 mm and 80 mm internal diameter, 50 mm height. So values of hydraulic conductivity were 6.4 into 10 power minus 4 centimeter per second, and also 4.35 to 10 power minus 3. So here two, as we know, two experiments are there for determining the hydraulic conductivity. One is a falling head and a constant head. You know what falling head and constant head methods are used. But then because the material here was so heterogeneous, we did not take a chance, and then we did both the test just to find out which one is there, and we usually adopted the worst value for designing. It's the same thing. Now, coming to the compressibility, what are the experiments that are used to determine the compressibility of waste? Why this thing is very, very important is like, as you know, soil is a material that is expansive. Some soils are expansive, some are not. Like say for example, clays are expansive, the other soils are not. Likewise, if you take the organic soils, like in this case MSW, it's expansive to a different degree. Means it is too very expansive. And then we have to determine the compressibility, means how well it can be compressed, or after compressing, will it again expand, or will it again come back to its original shape or size, something like that, in order to determine the capacity of the landfill, or in order to determine the other parameters. So this is very, very important. And when it comes to compressibility, there are a lot of different tests that we perform, like say for example, there are, as during settlement, there is primary settlement and secondary settlement. And in this case also there is a mechanical settlement, or that is called a creep, that settles very, very slowly, or that you know that the particles in that, like if you take a soil, then what happens is, due to the sulfate of the structure, or sulfate of the layers above, the particles, or the size of that soil breaks down, and because of that there is slow movement or slow settlement in the soil. So the same thing was applied here. And then when it comes to waste, again, like I said, some experimental knowledge is also required. We tried to find out what is this biological process that is also leading to the change in the particle size. So one is a mechanical thing that we normally study in geotechnical engineering, like one is the primary settlement and the secondary settlement. Here secondary settlement is a summation of mechanical settlement as well as the biological process. Like I said earlier, the waste degrades and the size of the particle is you know getting reduced as the time progresses. So we had to perform what to say, these experiments in order to determine the settlement due to primary compression, mechanical creep, and biodegradation. So I'll show how it is. So this is how it is. So the total strain here in this case is strain due to primary settlement, mechanical creep, and the biodegradation, like this. So these are the equations. We try to find out different equations, the equation for primary compression, secondary compression, and then the biological thing, and then we clubbed it all together. This is like developed, and the total settlement we tried to find out. So for this also we tried a setup, very small setup, then with a large setup. I'll show how it is. So experimental procedure is, whatever parameters we determine till date or till now, like the optimum moisture content, the unit weight, optimum unit weight, and the, what to say, specific gravity, etc., were used in designing this. So assessment of the primary consolidation was done by the triaxial consolidation tests. So now coming to triaxial tests, there are uh, different types of triaxial tests that are conducted to determine the shear strength. Like, one is called the consolidated drain test or consolidated undrained test. Consolidated. Why we say is that consolidated drained and undrained is that we check the failure during a condition when the whole of the soil is saturated or completely, drained or undrained. Drained is, when the water completely is drained out of the soil, and then undrained is when it is fully saturated. It gives us an idea, or it gives us a figure, values of, what to say, cohesion and, friction angle at which it will fail. So maximum load that can be applied, and then beyond which, if you apply, I think, the sample or the soil or whatever is there, it will fail. So those kind of tests were performed. So I'll just go into, a little bit of detail. So what is one dimensional consolidation? It's carried out using a odometer. I think people must have seen the odometer in the lab. I'll just show. So here, the normal size odometer is a different one. We used it 100 diameter and 25 height odometer. And, conducted tests on particle sizes of 4 and 10 and two moisture contents. One is optimum moisture content and one is a little bit, lesser than that, like 25 moisture content. So you can see the, I'm sorry. Okay. Okay, so there is some issue with the animation. So if you can see here, so this is normally the void ratio versus the pressure. So for the 44 moisture content and 25 percentage moisture content, you can see the two sizes, that is 60 and density, bulk density is 1.05 gram per cc, 4 10 you can see the almost zero. The worst part is, again it goes back, it decompresses because it is waste. So but then it, you can see at what pressure it compresses. So the void ratio is like, almost coming down from 0.7, 0.8 to almost 0.1. So that is how, it is. So what we can make out here is like, the applied pressure, if it is more than 1000 kilopascals or near to 1000 kilopascals, we can reduce the void ratios from, almost 8.8, 0.9 or zero point 0.7 to 0.1. Now, coming to the creep test, as I said, is a mechanical thing that goes on very gradually, and then we have to, wait for a very long time. So again, what happened here is the whole idea was to leave the setup once we load in a weight and just see what is the settlement. And once the settlement, what to say, becomes constant, only then the next additional weight will be applied. So that is a concept here. So we initially put some weight, say for example, we started with 57 kilopascal here, and then, we leave it for some time and we keep measuring the settlement day by day. And after a particular period of time, the settlement is constant. And that point of time, we double the weight, or, we increase the weight to 115, and similar processes follow. Again, after the settlement becomes constant at 115 kilopascal weight, then 230, then 460, then 960. So similarly, we'll see how much is the settlement. So I'll just show you so this is the setup. So you can see the setup. This is a, setup for expelling the water because of the pressure. So this is the setup. You can see the weights here. So as you increase the weight, this, pushes, or, pressurizes the waste inside this, mold, and then there are holes on top of this plate through which air can come out, or air will be expelled, and this part is there where through which your water can be, expelled. You can see this brown color thing, that is nothing but the water that was there in the, setup. So now, based on this, we also, try to find out what is the biological component. So you can see this results. Like I said, initially, the you have the, what to say, waste in that, and then you put this 57 kilopascal weight. Once you put that waste, you can see the strain that is happening. So this is measured in terms of strain. Settlement is measured in terms of strain. And then, once it becomes constant, you can see here there is not much, reduction. Then you put 115 kilopascal weight. Then you can see, once you put it, suddenly there is a drop. I mean, like, there is a higher settlement. And then again, it goes on. And there is a point where this is, constant, or, the settlement is very, very less. Again, at that point, you the additional weight or the double the weight, and then it goes on, and finally you can see that, whatever we saw there, like, how to correlate this is that, we had this 45 percentage moisture content in the waste, and you can see that, here the settlement or the strain is also around 40 percentage. Means that, the more and more weight you apply, it will compress, but then as you remove the weight, it will again, try to go back. So you can see the time that it takes, almost more than 100 days. So imagine this thing, if it has to be scaled up and if the same thing has to be applied in the field, how do we have to, apply it? So from this, what do we get is that, like I said in the equation, the total settlement equation, we try to find out what are the values. This is strain due to creep. You can see these values. So you will get these values. And from the graph, we'll calculate the C. And this is a time period for each and every waste. For example, 57 days, it was 34 days. 115, it was 20 days. Now what is B is the strain, like I showed in this equation. See, this is the values. C is the mechanical compression, and T is the time elapsed. D is the biological compression, likewise. So you will determine all these parameters, and once you determine all these parameters and you put it in this equation, or substitute in this equation, we'll try to get the total settlement due to primary, secondary, and biological consolidation. So coming to the total settlement, this is how, you can, now you will get a very good idea, like, because earlier I was telling about different experiments that were conducted to determine the settlement. Now you see the primary settlement is around, 15 percentage or 10 to 12 percentage, and this is the time in days. And then, it happens very fast, within a day, within a few, minutes or hours. And then the longest one is the mechanical creep, because it's very gradual. It takes more than, what to say, 50, 60 days, more than 100 days as well. And then, after that, whatever happens is your biological, biodegradation induced settlement. We wouldn't call it as a biodegradation settlement, but then biodegradation induced settlement. So it would be a combination of both mechanical creep and this thing. So you can see here also, total settlement comes up to around 45, 48 percentage. So this is the right way to find out a settlement for any organic soils, or in this case, waste. That would help us, because the settlements are the major reasons of failures in the geotechnical domain. Now if you construct anything on this type of material, because earlier what they used to do is, like, find a pit like area, or find a valley like area, you dump waste and then you just close it. But then you don't know how, solid it is, or how the foundation is. So unless and until you determine the settlement properties of those type of places, it will be very difficult to construct on that, or lay the foundation on that. Though we have a lot of other techniques now, like, micropiling or piling techniques and all those things, but still, determining the settlement of these materials is very, very useful. So this is the parameters. This is different studies that, that were conducted abroad, and then whatever parameters they got, and whatever parameters we got. You can see the settlement, in 4 particles is more, and the 10 particles is, around 45. So the surprising part is, like, this experiment was also conducted on 20, 35 particles, and the settlement varied around 40, 45 percentage, not more than. Okay. So what to say, this is an example of, MSW settlement evaluation. Like, if you imagine a 30-meter height landfill, and in which, a 3-meter layer is being formed, and then 10 layers are there. So the total settlement is calculated by substituting these experimentally determined values into the model, and then it is assumed that that let us construct this, like I said, 3-meter thick landfill or layer, and it is constructed in 50 days, and then total settlements with a lag of 7 days. You can see, you can calculate what is the, this is the settlement that is going to happen in the practical case, in that case. So you can see the time, it's like more than 10,000 days, or that is close to 20 years, 30 days. So you can see continuous filling, what is the case, filling with a gap of 7 days lag. This is what happens in a landfill, and then with a gap of 30 days. So you can see the settlement in meters. If there is a 30-meter landfill, the settlement is almost around to 10 meters. So if that is the case, then a huge failure will happen. This is like one more thing we try to see with the difference in thickness. Whatever it is, you can almost the total settlement is around 10 to 12 meters. So that is why it is very, very important to analyze these parameters before designing anything in a area where the soil is very loose, or where there is a organic soil, or where there is waste dump, or there was a waste dump, etc. Now coming to the shear strength characteristics of waste, this is like total settlement. um why shear strength is important is that there is a shear failure that happens. The shear failure happens if the cohesion is not good among the particles, and waste, anyways, it's not a homogeneous material, and then if it is not a homogeneous material, that the cohesion wouldn't be that great. And second thing is the friction angle. Friction angle among the particles of the solid waste is also one of the important parameters to be studied to check the shear failure. So just let us see what is that. So why is this parameter used? It is used for design of slopes, or vertical expansion of landfills, or seismic stability evaluations, and predicting failures. It's not just of landfills, even any geotechnical structure like um, um, remapping. So we also did the shear strength in the direct shear test, and we also did the traction test. So when we did the traction test, we also did the drained condition and in the undrained condition. So like I mentioned, in the drained condition, the shear behavior gives an understanding, or gives an idea about the long term stability, slope stability of the material. So the strength and stiffness also is one of the parameters that leads to determination of the stability and deformation, if there is any. So the elastic modulus that we understand in the soil domain also applies here. So we'll check what is the elasticity of this material, or organic soil, or waste, or whatever it is, and then accordingly it can be effectively designed. So there is something called as a what to say, the ratio, that is ES by sigma ratio, or E by S ratio, that is a effective vertical consolidation, consolidated what to say, elastic modulus. So like I said, the laboratory tests and methods, that is direct shear is the first test. So same parameters were used, like initial conditions, and then we perform the test, and this is how it is. You can see the material, how it is. It has a lot of components, like inert components, organic components, fiber components, soil like materials, inert like materials, etc. So the result is that measured cohesion and friction angle at 20% strains. Normally, what we do is, like in soil mechanics or geotechnical engineering, we limit all the what to say tests to 20% strain. And here also the same was followed. But then the surprise is that it doesn't fail at 20%. It even further goes beyond 20% strain. But then why we stopped at 20% strain is that the settlement is limited to 20% strain. So that is why after doing this test, we try to do the consolidated drained and undrained test. So according to this test, what we got is, like the cohesion is around 12 kilopascal, and friction angle is around 40 degrees. This is quite good, but then again, unless and until we check with the other tests, we cannot come to a conclusion, because some way or the other, this test kind of exaggerates or overestimates the values of CN5. So this is how it is. Like you see, we did it for three tests, 50, 100, and 150. So the strain, you can see, like I said, it goes beyond 20. So here is like, for generally for normal soils, you stop at 20, but then this doesn't fail at 20% strain. It even, it's more elastic. If you say in simple terms, it's more elastic compared to the soil, and then it just keeps expanding or compressing. This is how it is. Then we try to the, so you see that is so the what to say maximum correlation, or the R square value of 0.94 is obtained for 30% strain. Means that, the the values or the material is, at 30% strain, there is a proper positive correlation between the shear stress and the normal stress. Shear stress is nothing but one that is, applied from the side, or there is a stress from the sideways, or normal stress is that from the vertically above the material. So it's a now, because like I said, we couldn't get any proper failure, we try to see what happens with the triaxial test. Triaxial test is you apply the stress or the load from all the three directions, one vertically, one in the sideways, that is through your water, and when also from the bottom. That is why it is called, consolidated test, that is triaxial, all playing from all three axes. um, you know so we performed consolidated drained and undrained test. So here also the sample size were bigger because of the waste material. Normal size is 35 by 70, but then here we took it as, 50 diameter and 100 mm height. And the next one is like 100 diameter and 200 height, just to see what is the greater correlation. So for preparing the sample, there is something called as a static compaction and dynamic compaction. So, both the techniques were adopted for the, what to say 50 and 100 samples. Like, for 50 samples, the static compaction was enough, but then dynamic compaction was required for 100 samples. That is a big samples. Then if you see, then, again, like I said, 5 to 6 blows were applied for the dynamic thing. I'll show you the setup how it is. So this is how it is. This is the static, what to say, compaction setup that we designed it ourselves. Okay. And this is the, what is the dynamic thing. Once you close it, then you have this kind of, pipes on both sides to remove the air through this, and then keep compacting from the top. So this is the setup that I was talking about. It's a very interesting thing you can see here. Like, normal soils, you you put this, and then you can see the failure easily. But then here, what happens is that you place a porous plate on top of it for expulsion of water and air. So this is how it is. Surrounding the sample is the water. So you have your load from the top. You have your load in terms of water that is here, and then pressure that is applied here, pore pressure that is applied. That's why it is called a triaxial setup. So here I'm just showing you this setup. This is the actuator. You have your monitor through which you can apply your pressure, and then, what happens is that, it goes on as the load increases. There is a volumetric change, means the volume of the sample decreases as more and more air and water comes out of it, and then, finally at some point of the time it fails. So similarly, this was like, drain test, and then, similarly it was yeah. So similarly, undrained tests were also performed for the same, using the same setup, and then you can see the stress. I mean, like graph here. So this is a deviator stress that we call. So for different two units weight we performed, and you same 50, 100, and 150 kilopascal. So you can see that, it just keeps on increasing. At even at 20 percentage, it won't fail. The failure is nothing but the graph drops down drastically like this. You would have seen it in the soil cases, but then here it doesn't drop, and then it just keeps on increasing. You can see here. This is how, it just, goes on and on and on and on. So you can see the change in the values. Here it is, one is drained and one is the undrained one. So what we studied here is like, just to see the particle size effect on different parameters. So you can see here how there is a correlation between the shear stress and the strain, and you can see that, for the larger size particle, that is 10 mm particle size, it's somewhere in the middle. But then for the unit weight of what to say 10, and then particle size 4 mm, the stress is like more. It can means that it can take more stress. The larger the particle, the stress decreases, but then not decreases to a very low level. It's somewhere between 50 and 100 kPa. So the test also, you can see this severe stress. So at 20 percentage also, it doesn't fail, it just keeps on increasing. Same thing. And a similar thing, we try to see what is the effect of particle size. And this is again the same thing. You can see that, for 4 mm particle size, that's the maximum shear stress. And then, for the, what to say, particle size 10 mm and the lower unit weight, it is the least. The conclusion here is that the takeaway here is that, the higher the unit weight of the material and higher the particle size, what to say, higher the unit weight and lesser the particle size, your sample is good. So, try to keep the particle size as much as possible and then increase the unit weight. So variation in cohesion and friction angle, we try to develop a relationship between cohesion and friction angle. Anyways, for the soil, this kind of relationship is already established, but then for the waste, this type of thing is not established, and we were the first ones to do it in India. So you can see whatever happens, the cohesion decreases with the increase in friction angle. As the friction angle increases, the cohesion decreases. So the optimum would be to keep the friction angle, or the friction angle, at around 20 to 10 degrees. And during that time, friction angle variation in CD and CU test. So in a drain test, the friction angle is better compared to the undrained test. So the strength ratio and stiffness, this was like, like I said, experimentally, to determine what is the relationship between elastic resistance and the shear modulus. So you can see, like, as it increases, it's a linear relationship. And in both the cases, like normal stress and shear stress, one is like increasing, the other one is decreasing. So this will be used in designing the landfills whenever required. Like, for example, how it will be useful if, say, for example, we are having a what is a landfill of some height, and then, how much of weight comes on the bottommost layer. Accordingly, how it is to be calculated. Like I said, the strength and stiffness ratio here, it is like this. This is like, like this is how we calculated, and this was like, successfully applied to all the landfills. We even gave this kind of design to industries like Inalco industries, like, what is it, the fly ash industries or coal industries, for designing a containment system, even to the municipal solid waste management units at state level, etc. Like this. It was a S value and P value. So MSW unit weight 10 and at depth of 10 meter, shear stress and elastic modulus are like this. This is an example that is taken. Now coming to the dynamic properties, what are the dynamic properties? The dynamic properties are nothing but like the shear wave velocity or the shear modulus, damping ratio, etc. Why is it important to design or determine these things? Why? Because, if your base, or if your organic soil is in a very seismically active zone, then these parameters play a very, very critical role in the stability of the structure that you're building, or in the stability of the what to say, the overall unit there. So what are the field tests? Field test is like, MASW, multi-scale analysis of surface waves. Tests were conducted at 5 locations at a landfill site, and based on that, so this will give you, or this will determine what is the material that is there beneath through the shear wave velocity, and also it will give you an idea of the damping, that is there present at that level. Accordingly, we can design a lot of things. So okay, let us just show. Yeah. So this is how it is. I don't know whether it is clear or not. So these are all like GIFONs. This materials. So what will happen is there is a plate here at this point, and then when you hit the plate, the P and S waves, the P and S waves travel through this one horizontally, and as well as vertically. So both the things are captured, and then once both the things are captured, then we'll get a graph. I'll show you in the next slide. So these were the locations where it was conducted in within a latitude 1, 2, 3, 4, 5, like this. Right, try to see how the shear wave velocity passes through or propagates through the waste with different characteristics or heterogeneous as well as different moisture content at different levels. So this is how it looks like. So this is the area in Bangalore that was selected cell 1, cell 2, and different locations all over India. This was selected. I'm just showing one example. This is how you get this is the shear wave velocity with respect to depth. So you can capture close to 90 meters accurately. So you can see that there is a change in the velocity. So each and every material has a definite or a shear wave velocity within some range. That will be very very useful for us. Say for example, if there is a rock beneath, then the signature will be different or the shape will be different. If there is some water beneath the ground, then that will be different. So at those particular points it will change. So this will be very very useful in determining the type of materials. Then apart from this, to substantiate this, lab tests were also conducted. Now what lab tests is cyclic traction tests are conducted. Whatever we did earlier in the traction test, that was what to say, the static test. Here what happens is regularly it will be the load will be very very cyclic. So more than 70 traction tests were conducted in the laboratory. The shear modulus and damping ratios were calculated because the shear modulus and damping ratio curves were not present for the waste in India. So that was developed through this experiment. Again, the variation of these parameters are studied like confining pressures of 50, 100 and unit weights. Loading frequency was 0.1 and 1. That is the maximum, was case scenario that happened. With different moisture contents 35, 45, and 55. The samples were like 20 dia and 20. This was specially fabricated cells that were designed to carry out these experiments. So this is how it is. You can see shear strain, shear modulus, how it varies with respect to weight. The lower unit weight ones being or showing what to say, lower shear modulus and higher shear strain, whereas the higher unit weight material showing a little bit higher shear modulus and moderate shear strain. So the similar case was with the damping ratio. So now to put things in perspective, the shear modulus increased from 9 megapascal to 11 megapascals for 7.4 kilonewton per meter cube to 100. The damping also increased from from 4 to 20. Now coming to the degradation. So when the samples are collected, like initial samples, that is sample before degradation and sample after degradation, you can see huge difference here. That is with respect to the shear modulus and the shear strain. So the initial samples are very very what do you say, having high shear strain. The settlement is very high in those samples. You can put it as well like that. The strain is very very high in the samples, so the settlement is very high in the samples, initial samples. But then after degradation, after 1 year, you see the strain is very less, and the shear modulus is also higher. The thing is, like after 1 year, it would have degraded, and the mostly degradable thing would have gone in the organic soil or organic waste, and whatever is inert to some extent would remain, and that is why the strain is very less, or the settlement is very less than 1 percentage. And similarly, coming to the damping, the damping will be very very high in the initial sample. So you can see that it is like close to 15%. And here the thing is like the damping does vary with respect to the initial or degraded samples, because the holding capacity is like for both of them it's like more or less the same. But then the strain is like more in the the settlement is more in the initial samples. That is what I said. Coming to the confining pressure, effect of confining pressures, we see higher confining pressure has what I say, higher confining pressures, the shear strain is less, means that the settlement is less, and then as the strain increases, the shear modulus also decreases. Similar case is the damping ratio as well. Now coming this effect of this loading frequency. Why this loading frequency is important is that in a seismically active zone there might be different frequencies that might be active at different periods. That's why this test were conducted, and the output is like higher frequency, the damping is high, and then the shear modulus is also high. So the moisture content, similarly, you can see, the higher moisture content has, higher shear strain, or the sample with higher moisture content has higher shear strain, and the damping as well. So similar, thing. So there's a proper correlation between whatever we got. So you can see the normalized shear modulus reduction curve. Now like see the G by G max is called the measured shear modulus, and the strain that is happening here. So there are different techniques that differs for ways that is brought, but there was no such type of curve for the Indian base. So it's easy that the what do you say values of this all the triangles and these things. You can say it's a study. This is some study that was performed by Hub, and the triangles is the study. So somewhere in the word bound, near the word bound, this is the range. Why this is useful is like when you are what is it, designing thing, you are designing a containment unit. This dynamic what is a shear modulus or nominal shear modulus will be very effective in designing like how much shear can happen given the load or given the seismically active parameters. Similarly, the damping ratios also you can see ours is study or our intake based very also here around the damp around 15 to 20 or 22% with the shear strains of 1.1. It's very varies between that range. Now, whatever, I'll just give you an example, like, what did in the field, there is a software called Deep Soil, which is a one-dimensional software, and then, using that, we try to find out the, what to say, surface ground motion. Now, the idea was that there is a in a seismically active zone, what happens is that there is a distance somewhere beneath the earth, and that distance, just when it propagates to the surface, when it accelerates to the surface, it modifies or it just exaggerates or it just widens. So what is that acceleration at the surface and the ground? So those parameters were studied. You can see a graph here. This is acceleration and surface motion and input motion. So you give some input motion at some particular depth, and you see what is the surface motion. That is how this is studied. So these again tests were conducted. See this the surface motion, the acceleration, and immediate. So you can see that a rock it is much, and then for the other types of waste, as I use that figure 1, 2, 3, 4, 5. So you can see that it is almost all the so like this different spectral acceleration that are found out, and then what do they say? I would say that the peak acceleration is noticed before 0.5 seconds in the input as well as in the also, if you see the ground station, it is like less than 0.2 due to gravity. So what happens is that at the side there is a disturbance. So this disturbance is not normally or most of the times natural, but sometimes it can be due to work that involves high vibrational intensity or construction site. All these things also will need or can lead to these kind of activity. So it is very important to consider these parameters when you're working or when you're dealing with such kind of things. So here, the site-specific amplifications are to be accounted before designing something. In this case, a landfill design, or even if you are designing something like an embankment or a retaining structure or whatever it is, all these parameters need to be considered before getting into the design. to ensure proper reliable stabilized structures. So this is nothing but the same conclusions. Now, if you ask me the application examples, there are a lot of application examples. So there was a case where entire industries are come to us, and then they wanted a proper containment system designed for the red mud. Now the red mud is something that is the output of a bauxite ore mining process. Bauxite ore is mined, and then it is like what is the process and all those things, and then the waste that comes out is called. And what the important point to note here is that red mud doesn't have any what to say approved disposal characteristics of the earth because it is highly chemically alkaline in nature. The pH is around 11.5. It also has very components like sulfur oxide and aluminum oxide. And also there is other parameters that are very critical towards its it has very high what to say metals concentration like copper, lead, say nickel, cadmium, manganese. You can see the characteristics below here. So it's very difficult for such kind of material to get off or dispose of. So in this case, what we did is like we studied all the properties of this, like soil classification. What was the principles I suggested or I showed now. We carried out all the tests, for red mud. So instead of the waste, we the red mud and all these tests and we found these values like manganese and C5, what is the thing, moisture content, C or moisture content here. In base case it was around 5, here it was around 13.8. Soil classification, it's like a claims it is cohesion is equal to soil chemical reactive, stability is like 10%. So all these things, it is very important for us to determine all these parameters using your technical testing, and then based on this, then we decided design the containment location. This is how it was. So we just followed these CPCB norms of having a liner and they say a cup system, top and liner system at the bottom as per the rules and regulations, and we designed it like that so that doesn't fail. Hope you can see the structure here. Here raise and proper what is it level platform, and then again a raise, and then having a leachate collection system at the bottom because it has 13% moisture still. So that might seep in, and whenever there is a rain, some of the portion of the rain may also come into the red mud. Though we had discovered there are very high chances of leakage and ruptures of the solar system in the field. So we had also provided slope of 1:2 at the top, and at the bottom it was a bit more. And then we designed the system like this. You can see this. And then this was applied properly in the field, and then it actually very happy at that, and this we had we separated into CPCB also, and they have also accepted now it is being a as a part of the red mud disposal plan. For disposing mud containment systems can be designed using these parameters, and then it can be safely contained. So this is like just telling the application of geological principles in waste management. This is one thing. Then second thing is in these anaerobic reactors, it's a very big reactor. You have a gravel in place and level again at the bottom in the same rate as the field. We try to find out what is the settlement, what will be the maximum settlement, and what will be the maximum temperature variation if it is heavier. So the reactor, like they say, in the waste in the US is designed or to be designed to be in a landfill, which will generate the methane, and that methane is used to light up the cities or is being converted into electricity, and it is being used. So similarly, what we found here is that for the waste, settlement range is around 20 to 25%. So you have to take care of that, and the gas production is much. So the multiple thing is like all these things are happening in tandem or simultaneously here. There is a leachate that is coming down, the gas that is being produced at the gas house. So if you see all the three processes are happening simultaneously, and capture that, it's very difficult. At the same thing, we followed it in the field as well, and then we got similar values. So why I am telling this is like this is one project that we have got. Here also they wanted us to control the fire that is happening there, in the land. So there were still settled land which was huge problem. So there also we what it is like we use pressure principles, this is lab tests determine a lot of parameters like port pressure, and the other parameters like other conductivity, etc. And then we gave them a proper solution. Like there is something called auto ignition bulbs. It waste ignites because there is a generation of methane at a very high level, and then when it comes to the heat that is present in the landfill, while the heat in the landfill is around about 200 to 300 degrees. When the methane comes in contact, there is automatically some kind of recurring fire that's happening there. So again, we used our geotechnical principles to determine all these things, and then we said that if you maintain the temperature or the moisture content at 45%, and the temperature below 40 to 45 degrees, then there will be no fire, or there will be failure with respect to your because when the gas is produced and then it starts leaking, then it somehow creates like tap or what do I say, fissure. And then because of the fissure, there's a crack with the white pipe, and then there is a failure. This is how we determine the conductivity and specific heat of waste. The same conductivity principles or principles were used to something wrong with the conduction and convection principles. This is again the and there are a lot of other applications that we did, like we designed a continuous for consumption and deposition base. We designed a construction, mechanism for the what do I say, proper containment system for biomedical waste, for nuclear waste. All these things were done using the geometric principles, like concrete, two-meter thin concrete layer was used for kind of containing the nuclear waste. Again, there are also concrete properties that studied using geotechnical principles, like conductivity and other things. Similarly, for the biomedical waste also. So a lot of applications are there, even industrial grade hazardous waste, like fly ash, and there are a lot of other waste that comes from other industries, like oil or organic industries. Because again, those materials are taken and studied, and then as per the parameters, and then as per the values of those properties of the parameters, successful what is it, containment system design, and then we generated a lot of money on this because there was a lot of coming, even now it's coming. So this is something I just want to say that civil engineering, the branch of civil engineering like geotechnical, soil mechanics, and environmental engineering are now interrelated, and it can be successfully right. So what we saw here is application of geotechnical principles and techniques in solving a lot of practical issues and problems. Hope this is useful, and what we do when we do this in the lab is we realize the importance of this. When we go to the field, start doing or solving the existing problems or practical problems, only then we realize how important these tests and parameters are, and based on which how things can be done in a engineered way, or a scientifically engineered way. Thank you. Hope within the time or following time.
Yes, sir.
Okay. Any questions? You can even get back to me at a later stage if you have some doubts. Anyways, there's there, so get to me, not an issue.